Always taste in your mouth.
I'm joking.
But it's kind of funny, yeah. I mean, the way
have you put more than like 3 at once in your mouth before? Because I did it once. And I would describe the metallic taste. Possibly blood, probably not, but possibly blood.
All right.
My tongue was numb at the taste.
So, what we're going to be talking about today is percent dissociation. But there's actually a couple things in this that might shock you a little bit. So what percent dissociation is really this. Yeah, feel good. Sorry. So percent dissociation is really your 5% test. And it should make sense. When we're dealing with weak acids, they have low Kas. They don't do what? They don't dissociate very much. And if they dissociate less than 5%, we say we can make that handy-dandy approximation that makes the math easy. Does that make sense? So what you have here, this is essentially your X over your initial concentration. It should be HA, but. And that's exactly how we found our 5% test. So when you were doing your problems and you figured out the 5% test and you saw that it was 2.1%, what that means is 2.1% of the acid dissociated. Does that make sense? Here's something that might not make as much sense up front, but I'll kind of show you and give you some math to back this up. But it says for a given weak acid, the percent dissociation increases when the acid becomes more dilute. So what that simply means is less stuff means it dissociates more. More stuff means it dissociates less. You're probably thinking, well, that doesn't make a whole lot of sense.
Less water. I don't know.
Well, you can dilute things a couple ways.
Well,
And I'll get, after this first problem I go through, we'll give you an example of it, and then we'll kind of quantify why with looking at Q and some things. So,
because there's farther apart particle time?
no, it has to do with the stress on equilibrium.
Oh.
All right. So calculate the percent dissociation of acetic acid in each of the following situations. Based on that last bullet, that I know doesn't make a ton of sense up front, which one would dissociate more? B would. Okay? Now, let's prove it. Now, is it okay if I do the quick method of this? I'll tell you about that. I'll show you.
It's 1 to 1.
Yeah. Oh.
So what this ends up actually being, and since this is the same equation for each, we were to do our Ka.
It's a square root of that.
Yeah, it's essentially x squared over 1 and x squared over 0.1. Does that make sense? I don't want you to mindlessly do this without making sure that the situation allows you to do this. Okay? It's really important. So, when you take the square root of that, since you're just multiplying by 1, what do you get?
0.004.
Let's go to a little bit more sig figs than that.
4.2 times 10 to the negative 3rd.
You just said 0.004, that's only one sig fig out. I may be a little bit too much rounding. Okay, so the x is that. Now on this one you have to multiply by 0.1 and then take the square root. what after this?
Check.
Yeah, well, 5%. The 5% is our percent dissociation. So yeah, both really. Our change over our initial times 100, and our change over initial times 100 is our percent dissociation.
Wouldn't the weak point one?
Yep. Good call. Good catch. Everybody see that I made that change? Grant, what you get on the top percent?
142.
I guess you're just moving the decimal, so. Okay, so there's your percent dissociation. This was when you had a 1 molar, and this is when you had a 0.1 molar. And based on our mathematical evidence, it supports what it said. The more dilute it is, the more it dissociates. Now, I want to make this very clear. Just because it dissociates more doesn't mean that it gives you more hydrogen. Is that like, why do I say that?
It's less bucket.
Yeah.
Is that always true that it's going to be
Just like the ratio.
less hydrogen?
Yeah, like this dissociates less, but I had more to begin with, so I'm gonna do you see how I still have more H plus here than I have here?
Oh, it's true.
You see it?
Yeah.
This gives off more, but even though it dissociates less, it's because it was more concentrated. What's that?
Typically.
Yes. Okay? So be very careful in thinking that, oh, it dissociates more, therefore you're gonna have more. No, I mean take 0.42% of 1, it's going to give you more than 1.3% of 0.1. Okay?
It's a whole 0.9% difference. 0.9173766.
I mean, that's not a whole lot of difference, but
I guess not.
I mean, from an acid standpoint, probably. Yeah. Okay? So then, this is kind of the big thing here for this section today is what I kind of said. When you've got weak acids, your H plus concentration is going to decrease as your acid concentration decreases, but your dissociation is going to increase as it becomes more dilute. Another way of saying that would be as your acid concentration increases, so will your H concentration increase, okay? And your percent dissociation would decrease, it's just the opposite. Okay, so this is what I just stated, right? More dilute means what? Dissociates more, but what doesn't it mean? More hydrogen available. Okay, that's what this is saying. Okay? Now, let's kind of quantify this. Let's just say I've got this equation. Okay, and since it's a weak acid, we can say that the concentration of HF initially is approximately the concentration of HF at equilibrium. Why? Well, yeah, but why? since it's a weak acid,
It's left favored.
the concentration initially and the concentration at equilibrium are virtually the same. Why?
Just
It doesn't dissociate very much. So if it doesn't dissociate very much, they're going to be very close to the same number. Right? That's what this whole idea has kind of been about. I don't want you to get in the habit, I'm not picking on you, Rylan, but I don't want you to get in the habit of saying, oh, they're approximately equal because they're weak acids. No, they're equal because weak acids don't dissociate very much, and so therefore it isn't going to deviate much from the initial concentration. That makes sense?
So I guess it's the same thing as saying weak acids are left favored means they don't dissociate a lot because they don't react. They stay out on the reactant side. Is that kind of all really kind of the same thing?
Say that
Or-
slower.
The reason, well, not really the reason why, but because weak acids are left favored, they're also they don't dissociate as much because they stay reactants. It just means the same thing, just reiterating a different way.
Sure. Okay, and then we know that because it's a 1-to-1 ratio, the concentration of H plus is equal to the concentration of F minus, and we usually quantify that as X when we do our ice tables, correct? Okay, so if I were to set up a, you know, our table after we've done our ice table, it would look like that, correct? Whatever the Ka value is, X squared divided by initial concentration, because we'd be eliminating the X here, correct? Okay, so let's say we quickly dilute it. By a factor of 10. Okay, we quickly dilute it by a factor of 10. So what we can say is our new F concentration and our new H concentration are still equal, but it'd be X over 10. Why do I say that?
Less of it for a liter.
Yeah, if I dilute it, that means I'm adding, either I'm removing moles, which we're probably not doing here, or probably adding twice the, or 10 times the volume. So when we do concentrations, moles per liter, it'd be like dividing by a factor of 10.
It'd be adding solvent, right?
Yeah.
Okay.
Yep.
Okay.
Yep. Okay, so with that then, we could take and also say that my concentrations of my HF in the new conditions would also be divided by a factor of 10. So essentially what we're going to do then is plug that into here. But we know we're not at equilibrium because we diluted it. So we're going to call it Q. So can we find Q? So our new conditions would be X over 10 squared. And my initial concentration of my acid squared. But we can do some simplifying here. We can take these 10s out, right?
Yeah.
So it'd be, it would technically be x squared divided by 10. That would be gone, right? Because I'd only be able to get rid of one of the 10s. Does that make sense? Okay, and since it's really on bottom, I can actually put it down here. Well, what does this portion look like? Yeah, it looks like a
It
KA.
looks like the x over 10.
So Q actually equals 1/10 of your KA. So which way will it shift?
Right.
Is Q greater than or less than based on that? Okay? Your Q is going to be less than. So what you get is a shift right. And so all this to be said, when you take and dilute a weak acid, what it will do is it will cause the Q to be less than your Ka, causing it to shift right, and then shifting right is going to give us the reason behind why we see it what? Dissociate. Everybody catch that? When you dilute it, and the main reason here is we really only have one thing on the bottom and two things on the top, and so whenever you dilute it, you're actually just making the bottom bigger. Well, making the bottom bigger is going to make Q less than K, causing it to shift right and producing more product or dissociating more to reach equilibrium. Final thing here. Coming at it a little different way. As you may have found, this is going to be coming in, the proverbial back door. Not a problem you've seen yet, but it's just really the opposite, or similar to the opposite process of just finding your equilibrium, or finding your pH. So we got lactic acid. Is a waste product accumulated in muscle tissue during exertion, leading to pain or a feeling of fatigue. In a 0.1 molar aqueous solution, lactic acid is 3.7% dissociated. Calculate its Ka. Boy, they didn't tell us much, did they? They told us it's a 0.1 molar solution. So they told us virtually nothing. What do we do? Okay, so you're saying use the percent dissociation equation to find X.
Yeah.
Perfect. So we know X over our initial concentration, which they told us that, times 100 equals 3.7, right? So then you could just divide by 100, put that in decimal form. Solve for X. So for X is that, we know our Ka in this situation, everything's a 1-to-1 ratio, it's a weak acid, it's going to shift right, so therefore it would really be X squared then over our 0.1, and you would do what? Finish.
Solve for.
Put in your X and solve for Ka. Yep.
23.7.
Go ahead. Oh, you gave the answer?
Yeah.
No, you already did. Sorry, going too slow.
1.37
Huh?
1.37 times 10 to the negative 4.
Yeah. Now, this low Ka suggests that's a weak acid, like we would expect from the percent dissociation. Okay. However, it is probably on the stronger end of the weak acid spectrum. Questions? You're probably thinking this is easier than it actually is. The reason why I say that is we just keep adding little wrinkles. We keep adding little things that you got to remember when you're doing the math. The math isn't overly difficult, but if you don't process and what it is that you're trying to find the wrinkle of, it can become a little bit more difficult. I want to be fool's gold. You know. Okay, any questions? What was the main important topic of today then?
Percent dissociation.
When you dilute it, it